In this example, an FOC-based speed and torque controller is simulated using Altair Embed and Altair PSIM. Embed is used to model the FOC controller sections and PSIM for the motor converter sections. The two models are co-simulated synchronously using the Embed PSIM coupler block, which allows you to incorporate a PSIM model into an Embed model. The models are based on a Hudson M2310 PMSM motor with a built-in encoder and a Texas Instrument Boost XL 3pH GAN inverter. The PMSM motor model is based on the ideal rotating transformer, or IRTF concept. This concept can be used for both PMSM as well as brushless DC motors. The motor is driven by an AVS, short for average volts per sample, converter, which produces the three-phase voltages that are applied to the motor model. The AVS does not model the switching process. The FOC speed controller is designed to regulate either torque or speed, and it executes at 10 kHz. Navigating into the FOC speed controller block, the current regulators for the D&Q currents are contained in the current controller block. The SVM, or space vector modulation block, applies a modulation technique that improves DC bus voltage utilization by about 15% and reduces total harmonic distortion. The speed controller block is closed around the IQ current loop. The green crosshatch on the speed controller block indicates the block is configured to operate at a different update rate. In this model, we'll be using 1 kHz. Next, we'll make sure the model is operating correctly. The polar plot to the right is the result of applying the Clark transform to the three-phase voltages produced by the converter. When the motor is at rest, the current vector points vertically upward in red, and the flux vector points horizontally rightward in brown. The FOC maintains a 90-degree difference. As the current increases, the current vector amplitude increases. And as the current decreases, the current vector amplitude decreases. Scrolling down reveals the time history plots. The top plot is the phase A voltage in red and current in blue. The second plot is the motor shaft torque. Its response is smooth and well behaved due to the AVS. And the third plot is the motor shaft speed in RPM. The set point speed is 2000 RPM, so it's going to take a minute to reach that value. Now we'll move to a more accurate co-simulation that uses Embed to model the FOC speed controller, set points, and plots, and PSIM to model the motor and a switching converter. The two applications are connected and synchronized by the PSIM coupler block. This is an Embed block used to incorporate a PSIM model. Navigating into the PSIM coupler block, you can specify the PSIM model to be used, and you can edit the model if necessary. The switching converter is entitled GAN INV module. The switch controls come from the PWM unit directly below the inverter module. The PWM inputs are provided from the FOC speed controller in the Embed application. The three voltage measurements are on the lower right section of the schematic. Above this section are the shunt resistors, which provide the voltages corresponding to the three currents. The PMSM motor is an IRTF type. Okay, let's run our model with speed control active. On the polar plot, you can see the switching behavior in the red current vector. As the speed increases, the torque ripple increases. Let's zoom in to get a better view of the torque ripple. Zooming in further on the phase A voltage plot shows the switching process in blue and the average voltage per sample in red. Assuming the transient and steady-state torque and speed responses meet your requirements, the next step is to use the Embed Auto Cogen feature to create firmware for the FOC speed controller and test it on your target microcontroller. We'll save that for a future video. Please visit the Altair Embed website located at www.altair.com/embed for more examples and free trial versions. Thank you.